Hello everybody. So now after discussing the heat of reaction method and the heat of formation method, the next thing that I want to mention, which is a very important thing to mention here, which is are these two methods going to give us the same numbers or not? And if yes, how comes? So the answer is yes, they are gonna give the same result, and I'm gonna discuss it with you here because it's an interesting thing. So what we have here is the terms that we have for the heat of reaction method. I put everything together. This is the delta H1 for oxygen, for nitrogen. This is the heat of reaction, the extent of reaction multiplied by the heat of reaction calculated from the heat of formation. This is the excess oxygen in the product. This is the nitrogen in the product. This is carbon dioxide in the product. This is the water in the product. So this is delta H1, this is delta H2, this is delta H3. In this case, this is the delta H1 for carbon dioxide, this is delta H1 for oxygen, delta H1 for nitrogen. So this is the first part of the heat of reaction, the delta H. The second is the oxygen, the product, nitrogen, the product, carbon dioxide, the product, and the water in the product. So starting from here till the end is delta H2. I want to compare the terms that we have in the two methods just to show you why we have the same result. So if you look here, you'd see that we have 600 carbon dioxide from 300 to 25. You have 2256 nitrogen from 300 to 25. This term is the same, 300 multiplied by the heat of formation of carbon dioxide, 3 multiplied by 100. 4 multiplied by 100, 4 multiplied by the heat of formation of water, negative 1 multiplied by 100, which is negative 100 multiplied by the heat of formation of propane. 100 multiplied by oxygen from 25 to 1000. You have 2256 nitrogen from 25 to 1000, same number. We have here 300 multiplied by the Cp of oxygen from 25 to 1000, and 400 multiplied by these three terms, which are the same three terms. So if you look at the two equations, or the two sets of calculations, they're exactly the same but arranged in a different way. So whether you go for this method or you go for this method, you are going to put the same calculations. No matter which method you are using, it's just how you arrange your terms in the equation. So now comes the question, which one should I go for? The heat of reaction method is more favorable if you have one reaction and you know how to calculate the heat of reaction. This is how you will be looking at the heat of reaction method, or when it's better to use the heat of reaction method. If you have multiple reactions, you will have more than xi delta HR. You will have xi1 delta HR1 plus xi2 delta HR2. So if you're going to go for this method using multiple reactions, this is going to take more time. For the heat of formation, it's also favorable if you have more than one reaction, or if by somehow you are not able to calculate the heat of reaction. So anyways, these two are the cases that would make the heat of formation more favorable. There are some examples in the textbook that are helpful that you can try. They are already solved, 951, 952, and 953. And I already have an Excel sheet containing the calculations for these methods, and I'll include this in the I'll share the link to this Excel file in the video description. It's helpful just to see how the calculations are made and to see the numbers one by one. This is the first. You have only one reaction, and in this reaction you have ammonia oxidation or combustion of ammonia to produce nitrogen oxide, water, and oxygen. So this is one method. You have here two reactions, and in these two reactions you will have methane oxidation and combustion. So this is one other method. And there is one last example, and I'll be solving this example because in this example we have an adiabatic reactor. We haven't solved an adiabatic reactor in the all the previous cases are isothermal. So you have Q, So there is heat in or heat out of the reaction. This is a case where there is no heat in or out of the reaction. It's going to be very similar, but we will do this, I'll solve it in details next time, just to show you how this method, these type of systems are solved. We solved it before at the end of chapter 8, if I'm not mistaken, or chapter 7, I'm not sure, an adiabatic heat exchanger. So it's going to be very similar to this. An adiabatic system will require some calculations that are not as easy as the previous cases. So this is what I'm going to be doing next time, inshallah. So I'll see you then. Goodbye.